I'm Collin Litterell. I'm a PhD student at the University of Washington, and my advisor is John Palmieri. I want to talk a little bit about my research, which involves a classification of the thick subcategories of modules over the Steenrod algebra. So first, a little background. The story really starts in stable homotopy theory, where the central goal is to compute the stable homotopy groups of the spheres. Now, of course, this is a very hard problem, but a lot of progress has been made in understanding algebraic structure here. And so one example of this is in the late 70s, Miller, Ravenel, and Wilson showed that P locally, the stable homotopy groups of the spheres, can be broken up into periodic chunks. So we get a Vn periodic piece for every non-negative integer n. And a little after this, Ravenel conjectured that this algebraic periodic structure was really just an algebraic manifestation of periodic structure in the stable homotopy category itself. And this was proved by the work of Devenath, Hopkins, and Smith. And one theorem which illustrates this idea nicely is the thick subcategory theorem. And this says that if we look at the stable homotopy category of finite P local spectra, the thick subcategories are, as displayed in this picture, we have this nice chain where each Cn is the full subcategory of Kn minus 1 acyclics. And we should emphasize that each of these Cn's is intimately related with Vn periodicity. And so this thick subcategory theorem is telling us about the global periodic structure of the stable homotopy category. Okay, so this theorem inspired many others in various other fields. For example, in commutative algebra for the derived category of a ring, and modular representation theory for the stable module category of a finite group or group scheme, and in many, many others. And the general setting in which all of these theorems take place is that of a tensor triangulated category. And a tensor triangulated category is just a triangulated category with the additional structure of a symmetric monoidal structure, which is compatible with the triangulated structure. Okay, so given such a thing, a nice tensor triangulated category, we can construct something called the Balmer spectrum, which is a topological space, and it comes equipped with a collection of closed subsets, one for every object, called supports. And these supports satisfy some nice properties. And one of the key features of the Balmer spectrum is that computing it as a topological space is equivalent to classifying the thick tensor ideals of T. And I'll just say in many cases, thick tensor ideals will be equivalent to thick subcategories. Okay, so now I'd like to focus on the mod 2 dual Steenrod algebra, which is of course a very important object in homotopy theory. Just algebraically, it's a Hopf algebra, and its algebra structure is, well, it just looks like polynomial on infinitely many generators. And one of its key features is that if we look at the mod 2 homology of any space or spectrum, we get a co-module over A. And then one of the main computational tools in stable homotopy theory is the atom spectral sequence. And we see on the left-hand side, we have something relating to A and some co-modules over it. And then on the right-hand side, we have homotopy classes of maps. And so sort of the idea here is that if we can better understand the dual Steenrod algebra and its co-modules, then this should lead to better understanding of stable homotopy theory. Okay, so now going in almost the reverse direction, we can use tools and techniques from stable homotopy theory to study the dual Steenrod algebra and its comodules. A little more precisely, there's a tensor triangulated category, which we call stable A, in which we can do stable homotopy theory. So some basic analogies, we have a sphere object, we have a smash product, we have homotopy classes of maps, we have stable homotopy groups of spheres, and so on. We also have things like Brown representability, Gauss field localization, etc. So an example of a theorem proved from this point of view is an important theorem of Palmieri, which says that there is a single object, HD, in stable A, which detects nilpotence. So this is analogous to the nilpotence theorem of Devenatz, Hopkins, and Smith, and it's sort of suggesting that we should think of HD as playing the role of MU or BP. And so in light of this, we can consider the Hopf algebroid, where we look at the homotopy groups of HD and then the HD homology of HD. And this is analogous to the Hopf algebroid BP star, BP star, BP. And the key idea in all of this is that BP is playing this very important role in understanding the global periodic structure of the stable homotopy category. And we should expect HD to do the same in our category of A comodules. So to really highlight the analogy here, we can rephrase the thick subcategory theorem of Devenatz, Hopkins, and Smith as a computation of the Balmer spectrum in terms of invariant prime ideals in BP star. And the idea here is that the Morava K theory Kn can be thought of as sort of a residue field of BP at an invariant prime ideal in BP star. And so we can try to do something similar in stable A, where we start with HD and we try to take a residue field at an invariant prime ideal in HD star star. And it turns out that we can do this with some help from some techniques from modular representation theory. And we get a collection of field objects which jointly detect nilpotence. And so in this way, these KPs are very analogous to the Morava K theories. Okay, and now with this, we can carry out a computation of the Balmer spectrum of the finite or compact objects in stable A. And we get that the Balmer spectrum is the invariant prime ideals in HD star star, which is a very nice analogy with the original story. And as we mentioned earlier, this is equivalent to giving a classification of the thick subcategories. And so this is sort of describing the global periodic structure of this category of comodules over the dual Steenrod algebra. Okay, so that's all I want to say for now. Thank you for your time.